Okay, finally on to the last question here, and it's a bit of a long one, so bear with me. So, starting off here, it says the source code for a file name whoops.c is shown below. When it is compiled and run as whoops.exe, the stack is shown in the diagram below. So it's giving you what that stack looks like. We've got return address prior EVP, we've got the variable name here, and then we've got hometown here. And if we look at what this does, we call func with argv1 and argv2. So those are command line arguments. They're going to be passed in as strings, and we're assuming that they're being passed into this function as pointers to characters, and then they're being string copied from name var, which is argv1. So the first argument is going into name here on the stack. So we can maybe label that this is argv1, and then the second one is going to be argv2 up here. That's going to go into hometown with this string copy. So just analyzing the code a little bit to understand what's happening and have a better idea for later on what's going on here. So first off, suppose the user executes this file with command line arguments whoops.exe, AAA, BB, CCCC, etc., and then Cali. So important to note here, what's happening is we're going to write a bunch of stuff into name, and then we're going to write Cali into hometown. Both of these are 28 characters long. Here we've got 4, 8, 12, 16, 20, 24, 28, 32 characters that are going into name. But it may or may not matter. So let's see how much space we have on the stack for name. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. And each of these boxes, if we see it, the addresses over here, there is some padding on the stack. So we actually have 4 times 4 bytes per box in this case, and then times 9 boxes, we actually have 36 bytes for name. So we need to have 36 bytes to sort of do anything wrong. So when we enter this, we string copy these in, and we say welcome %s from %s. So our output is going to be welcome, and the first %s gets replaced by name. That came in as AAA, BBBB, and I'm just going to put dots there, but it's this whole thing goes here, right? And if you see that it is that way on the solution, hopefully that helps. And then Cali, or from Cali. So we're going to have this whole long string, welcome that from Cali, and it sort of works because we have enough space to store names so we don't overflow prior EBP or return address, and hometown is up here so it doesn't get overwritten. And that's hopefully a little bit of guidance for the second problem here, which is suppose the user executes this file with command line arguments whoops.exe fred and then AAA, BB, CCCC, etc. So now Fred is going into name. So we're going to take up this space here, and that's going to be what we have in name. And then hometown is going to take this huge argv2 that we're passing in, which is going to be AAA, BBBB, CCCC, DDDD, E's, F's, G's, and the H's that we put in when we string copy those, that's going to actually overwrite Fred. And then we're going to end up with the null terminator after that. And so what we're going to get when we print to the screen is welcome HHHH, because that has overwritten Fred and we have a null terminator there. And keep in mind, printf keeps going until it finds a null terminator for a string. And so we have welcome HHHH from, and then we're going to have this huge string here, starting AAA dot dot dot, and that's going to end up finishing with HHHH, because again, it's going to print the whole way down here through HHHH till it finds a null. So we've sort of overflowed hometown into name when we string copied because it was too large, and then we also overflow reading into name whenever we print it, because the null terminator is somewhere in name, and it's going to keep printing until it finds that null terminator. So that's the first two, really just assessing, do you understand how a buffer overflow works? And it's important to note here that, if you see a buffer overflow question on the exam, you should assume that something weird is going to happen, right? Buffer overflows are not how a program is supposed to execute or supposed to be executed. So if it looks like there might be an overflow, assume that something weird is probably going to happen as part of one of these questions. So on to part C. What are the minimum number of characters to enter in the first command line argument, e.g. argv1, in order to cause a segmentation fault? So looking at argv1, I already sort of counted this out. We're starting here. That gets copied into name. So we're looking at 4, 8, 12, 16, 20, 24, 28, 32, 36. So 36 bytes until we get to prior EBP. So 36 characters have a, characters plus the null will cause a, segmentation fault, likely because we're overwriting part of prior EBP. So 37 bytes in total. Keeping in mind that if I enter 36 characters on the command line, if I entered a, HHHHIIII here, that would be 36. And then that null terminator happens automatically at the end of a string. And so we would have 37 bytes worth of data that would write into the first byte of prior EBP with a 0, 0. So it would overwrite something important, which is likely to cause a segmentation fault. So that's the first couple parts. Let's flip on to the next page. And this goes into problems where we're trying to understand what a successful exploit might look like. And you'll see you're provided with a stack again, a blank one to understand what's going on here. So suppose the same code is now copied and compiled into 3 exe files, which are all the exact same except for different file permissions as shown below. So we're still running the same code. We're still doing the same thing here. We still have the same buffer overflow potential, but we have different command line permissions that might factor into what's going on here. So, and give me a second here to try to adjust my video camera because I see it's not focusing quite as well as I'd like it to on this. There we go. It's a little better. So for the first one here, it says suppose user Ken creates an exploit with 24 bytes of shellcode, which opens a shell prompt, a NOP sled of 24 bytes, and a malicious return address of BFFF308 repeated 30 times. The user Ken runs the following command line argument, where exploit here denotes the entire exploit, the shellcode, the NOP sled, and the malicious return address in appropriate order. And we'll have that command line where he's putting the exploit into argv2. So keeping in mind from what we did on the first page, argv2 is going into hometown. So the exploit is going into hometown. So we're starting all of that here. Okay. So first off, does the exploit code successfully open a shell prompt? So what we need to do here is sort of work through this setup and understand what's going on here. So keeping in mind that the way we usually run a buffer overflow is we have the NOP sled, then we have the shellcode, and then we have the repeated malicious return address. So repeated MRA. And so that's what we're looking at as the format here, and let's go ahead and write that out on our diagram to see what's going on. So we're going to write in the NOP sled. So this is a NOP. We have 24 bytes of that. So it says NOP sled of 24 bytes here. That's what we're putting into these boxes. So we're going to have 1, 2, NOP, NOP. That's 12, 16, 20, 24, 28. So that's our NOP sled that goes in there. We have 24 bytes of shellcode. So shell 8, 12, 16, 20, 24, 28. So 24 bytes of shellcode, and then we repeat the malicious return address, BFFF308, 30 times. And so we're going to have, I'm just going to write out MRA here, malicious return address. And we'll see that, it continues on for another, this is 16 bytes, or, 16 or 4 times worth of it. It's going to go another 30 times, so, 26 more times. And we're trying to assess, does this work? So the first thing we have to check for does it work is, does the return address get overwritten by a malicious return address appropriately? And in this case it does, because we see that a malicious return address has replaced the original return address. The computer is just sort of going to blindly take whatever value is here, and that's where it's going to return. Next, we want to check, does the actual malicious return address that was provided, so this BFFF308, does that point somewhere into the NOP sled or at the very beginning of the shellcode? The only final case that we can do is to point to, basically we have to point to at the very top of 31C or somewhere in there. So does BFFF308 fall there? We can see that it's right here. So we succeed in the second condition. So the idea, again, is that we go to the return address that's now the malicious return address, which is BFFFF308. So instead of going back in the text segment where we want it to, where the original code wanted it to go, we're going to go to this address, which is now a NOP sled and then some shellcode. And so the NOP sled is sort of a safe landing zone. It's just nothing. And so we can fall into there and then go down. And then the shellcode gets executed. And so this is going to work. We're going to land in the NOP sled. We're going to move down to the shellcode, and we're going to execute it. So this is a yes. It does work. And then let's look at the next question, which is if the shell prompt is open, whose privileges did it open with? So we're saying that Ken runs this exploit. We want to know who does he end up with permissions as, and we're assuming that Ken is part of some group potentially. Let's look at the permissions, and sorry if it's a little hard to see, but we've got execute permissions for everyone, so we can always run this, and that's for whoops v1.exe. And you'll see that it's kind of highlighted here, and that's because it would be in red background in the terminal. That's an important thing to know, is that whenever we look at something that's highlighted in red, that means it has the set UID permission on it. And that's considered dangerous, so Linux kind of shows you that it's dangerous. And we can verify that here looking at the leftmost group, which is the owner's group, right? That's midshipman's permissions. And we see that it's read, write, and S, which is execute with set UID. So whenever Ken runs this program, which he has permission to execute it, so he has X in either students or public, so everyone can run the program, he becomes the owner while he's running that program. So if he opens a prompt, it's going to be midshipman's prompt. And that means he can do whatever midshipman can do on this system now. And so the explanation here, you might want to write something that, the MRA, malicious return address, covers the original return address. And the MRA points to the shellcode or NOP sled in memory. So the exploit works, and here we have for the second one, the set UID flag is on for whoops 1 v1.exe, and midshipman owns the file. Okay, so that's what we're looking for on the first question here. Let's move on to the second one. So suppose that user Ken creates an exploit of 24 bytes of shellcode, which opens the shell prompt, a NOP sled of 24 bytes, and a malicious return address of BFFFF318 repeated 30 times. User Ken runs whoops v2.exe, Fred, and then exploit here. So we're doing the exact same thing. Ken is running this code. It's the same thing, except now we have a return address of BFFFF318. So we still have 24 bytes of shellcode, NOP sled of 24 bytes, but now we're returning to 318. So if we look here on our diagram, BFFFF318 is still sort of in our safe zone of the NOP sled. And so this should still work correctly. We should be able to run this code. We're running whoops v2 this time, so let's look at the permissions for that. So it's going to run as root, or the owner is root, the group is root, but everyone has execute permissions on this. So this is sort of a vulnerable file here. It's really not usually a good idea to have something that's owned by root, a group of root, to then have other people allowed to run that program. But here we see that it does not have set UID. It's just RWX for the owner. So everyone has permission to run it, and everyone has permission to read it. But if Ken runs it, he's just still keeping his own permissions. So Ken does not become root with that, and that's what you would want to put into the explanation here. Is that the MRA still overwrites the original return address, and the MRA points into the NOP sled. And again, to note that the last place that the malicious return address can point to is the very beginning of the shellcode. As long as it points, it could be 31C, and that's the start of the shellcode, so that would also be okay. Though you're really kind of cutting it close at that point, that you might get into trouble here. Actually, it looks like from looking at the solution, I may have done one too many of these. Yeah, I did one too many nops. So actually, the shell should be here. And that's my bad. So that is actually what this is testing. And this second question is that the shell code is there. And this should be the MRA then, starting 1 byte sooner. So I was off by 1 when I put my answers down here. But this is the same basic exploit, just a different return address, and it is pointing to the shell code instead. And then analyzing that the permissions now have root as the owner, but no set UID. So let's look at the last one here. Suppose that user Ken creates an exploit with 24 bytes of shellcode, which opens the shell prompt, a NOP sled of 12 bytes, and malicious return address of BFFF320 repeated 30 times. Suppose they have a different order for the command line arguments, putting the exploit first. And then let's see what happens with this. So here, we're going to go ahead and copy in. The exploit here is going to go into name, in this case, instead of hometown. And the hometown is going to just get Cali, right? Because it is above name on the stack, and so it's going to not overwrite anything. Name is going to be where we start this, and so we have 12 bytes of a NOP sled, keeping in mind that we sort of have NOPs, and then shell, and then MRAs, malicious return addresses. And so the NOP sled is going to start here. We've got 12 bytes of it, so 4, 8, 12. And then we're going to have 24 bytes of shellcode again, so 4, 8, 12, 16, 20, 24. And then we're going to have malicious return addresses repeated 30 times. So, that, and then 28 more times is what we're going to have in memory. And so now let's do the same thing, analyze what's happening here. So we see that the real return address is overwritten by the malicious return address, and that malicious return address is BFFF320. That's pointing to here, which is in between our NOP sled and our first line of the shellcode. So it is going to be successful again, and we can say that the MRA. And again, I would say here, maybe don't abbreviate this, say the malicious return address on your exams. I'm just doing it for, clarity and to be quick here. So MRA overwrites the original return address. And points into the NOP sled. And so that, yes, it's going to be successful again. Now we need to loop back and look at the permissions for this. So we know that the shellcode works. Let's look at the permissions for this whoops v3, which is the last one here. It's again owned and group is root. Owner and group is both root. And now we see that everyone has execute permissions, so it's important to make sure that if the owner and group are root, that the public group does have execute here. Otherwise, they can't run the program anyways. So Ken couldn't run the exploit if he can't run the program. Here we have set UID, and you notice that this is highlighted again. It would be in red if we're in the terminal. So it's set UID, which means when we execute it, we're going to execute this as root. And so that means Ken gets a root prompt, which is what he's looking for. So, so the terminal opens as root because it runs with set UID. Owner is root, and public has executable privileges, or execute privileges. And that's it. That was a long question, but that's the idea. That's what we're trying to get across here, is to understand what's happening in memory whenever we run one of these buffer overflow exploits. So I hope this helps. Good luck.